Okay, before we start, I just would like to confirm that you guys can hear me. Okay, perfect. Thank you guys so much. How do I know if my mic is on? You don't need a mic. Okay, cool. I think we can begin. Okay, so Assalamu alaikum and good morning to one and all. For those of you who don't know me, my name is Abdullah Ali. I'm going to be your guys' tutor for physics, grade 12 physics for the rest of this year. He's brain fart. Okay, so for today we'll be starting us off with momentum and impulse, the first topic for the year. Yeah, eventually we'll get to like vertical projectile motion and organic chemistry. Okay, that's for chemistry. I know you guys are probably there in school. You guys are probably doing that. But yeah, for now we're going to start off with momentum and impulse. Okay, for those of you who are not joining for maths, if you do have any questions, please feel free to leave them in the Q&A or the chat. Right? And cool. So let's get started. And one more thing, the notes that we do, all the notes that we do will be sent in the group. You are free to take notes if you'd like, but all this entire PDF will be sent on a Google Drive in the group latest by the night of the lesson that we do. Okay. Okay, so we're going to start off by first going through momentum and its definition. Okay, so momentum is defined as the product of an object's mass and its velocity, and we can see the defining formula, P is equal to M times V. Okay, where P is actually the symbol for momentum. Okay, we have mass, M, which is mass, and V, which is velocity. Okay, in this formula, okay, provided that our mass is remaining constant, we have a relationship created between momentum and velocity, and we say that momentum is directly proportional to the velocity. So basically, the higher the velocity, the higher the momentum, and vice versa, provided our mass remains constant. We're dealing with the same object. Okay, let's move on to impulse. So impulse defines as the product of the resultant or net force acting on an object and the time that the net force acts on that object. You'll see we'll go through that definition. Okay, but impulse more simply can be defined as the change in an object's momentum. So impulse, the symbol for impulse is delta P. So for momentum, we have P, and for impulse, we have delta P. So impulse is the change. Remember, delta in mathematics, in physics, represents change, final minus initial. Okay, that's what the delta represents. So change in the object's momentum is delta P, that is known as impulse. Let's have a look at our formulas. Okay, so firstly, remember we discussed that change in, delta P is impulse, and change in anything means final minus initial. That's why change in P represents final P minus initial P, meaning final momentum minus initial momentum. Okay, we utilize units for momentum. We can use kg meters per second to the -1. Okay, we'll go through the other one that we can use. For mass, we use kgs, and for velocity, we use meters per second to the -1. Okay, so this is our first formula for impulse, which is basic, but it's important to know because it's easily forgotten. And when the question comes where you have to do something simple as final minus initial, it's easy to forget. So this formula is important, okay? Then we have the next formula, which is delta P is equal to M open brackets V final minus V initial. So this is basically the same formula. Okay, I'll show you how. When we talk about P final minus P initial, we need to remember that the actual formula for P is what? M times V. Okay, so this is M times V, and this is also M times V. So P final minus P initial could also be M V final minus mv initial. Okay, so the mass times the velocity final minus the mass times the velocity initially. Okay, because we are dealing with one object, as we'll discuss in a second, we are dealing with one object, the mass is the same, and we can take that mass as a common factor. And that's how we arrive at this formula. Okay. Now, when it comes to this formula, it's one of the main formulas that we use almost all the time. We need to note that direction is very important. Direction is extremely important. Okay, we need to note that. So, okay, maybe we'll, yeah, okay, let me just move this over. Okay, direction is very important, right? Why so? Because remember, when we deal with, I'm not sure if you guys have dealt with vertical projectile motion yet, but when you're dealing with a direction, it is represented by a negative and a positive. In physics, okay, compared to maths, let's talk about maths first. In maths, when we talk about -5 and 5, when we talk about -5 and 5, -5 and 5, we can clearly say that 5 is bigger than -5. It's 10 more units bigger than -5. However, in physics, that's not the case. When we compare -5 and 5, okay, they have the exact same magnitude. However, the negative would indicate direction. So if one is positive, one is negative, that would mean that they're in opposite directions, whatever it is, right? It depends on the question, depends on which topic we're working with, but it could be east, west, north, south, okay? But positive and negative, opposite directions. So that's why in this case, direction is extremely important, because when we are inputting values for velocity, which is a vector quantity, okay, we remember from maybe like grade 10 that we learned it first, that we talk about scalar and vector. Scalar contains only magnitude, while a vector contains magnitude and direction, and that's where the negative and positive come in, right? So velocity, our friend here, is a vector quantity. So it has direction, okay? So some velocities could be 20, some could be -20. Okay, some would be positive, some would be negative, and we need to input the correct one, being is if it's negative or positive, and of course the correct magnitude. Now, one more thing about this formula is that the V final, okay, in momentum, you'll see we deal with collisions, okay, crashes, when two objects collide, when something knocks the other one, however you want to say it, but we deal with collisions, right? Okay, the V final is actually after collision, and the V initial is before collision. Again, these notes will be sent to you guys. V final after collision, V initial before collision. Okay, I have a question. Can you please differentiate between impulse and momentum? Okay, how would you know what to work with to calculate, and what is the difference between the two? Okay, fair question. So how would you work with, we'll get to that when we do questions, right? The question will specifically ask calculate impulse, or alternatively calculate momentum, which is not that often. Okay. The simple answer is, the difference is, when we talk about momentum, we just think of the formulas for them to define them. So when we talk about momentum, we talk about P is equal to M times V. P is equal to M times V. An object's momentum is the product, the multiplication of its mass and velocity. So that is momentum. But when we talk about impulse, impulse is a change in momentum. So whenever our momentum is changing, that's when impulse is created. So yes, both have the P, but impulse has the delta, which has the triangle, and that's its key difference, meaning that impulse is actually P final minus P initial. So impulse is very closely related with momentum, because actually impulse is when you take the final momentum of an object and the initial momentum of an object, that gives you the impulse. So that's what impulse is. So the difference is, one is momentum, okay, and one is a change in momentum, which we could have called change in momentum, but it is called impulse. Okay, it's just another word of saying change in momentum. That's the difference between the two. Again, when with regards to when you should use what, it will be stated like blatantly in the question. Calculate this. Calculate the object's impulse. Calculate the object's momentum, or the momentum will be given, or the impulse will be given. Okay, and yes, when we deal with these formulas specifically, all of these formulas are impulse formulas: delta P, delta P, delta P. But we need not forget that delta P is the change in momentum. So that's how they relate to each other. So while we have delta P is actually final momentum minus initial momentum. Okay, so that's how they relate. Okay, so yes, we're discussing this formula. Direction is very important. V final is after the collision. V initial is before the collision. And we have the last one, which is delta P is equal to F net times delta T. Now, these two are the most important ones. If you've maybe done already a lot of examples, you'll notice that you combine these two a lot. Okay, so the next one is delta P is equal to F net times delta T. That's actually the defining formula. The definition is the product, which is the multiplication of the resultant or net force, same thing, the product of the net force acting on an object and the time that the net force acts on an object. That's this formula here, F net times delta T. Okay, so yes, that's another formula to calculate impulse. Okay, remember impulse is change in momentum. So impulse momentum is related to impulse. Okay, then if we rearrange that formula that we just discussed and we write it as F net, it's actually another defining formula, but this time for F net, for net force. So F net is equal to delta P over delta T. So force can also be defined as the rate of change in momentum. Okay, you must always remember again in physics, whenever we deal with delta T, this is a rate of change. Whenever delta T is in our denominator, this is a rate of change of whatever's on top. This is for chemistry as well. Okay, and remember that all of these formulas are for one object. We're dealing with, for each object, each object has its own momentum, each object has its own impulse. Okay, cool. Now we're going to talk about a concept called conservation of linear momentum. So does it mean we can use, I have a question. So does it mean that we can use any of these formulas to calculate momentum? Okay, that's a tricky question, right? It depends on what you are given in the question. Okay, what formula you're going to use depends on what information you have in the question. Okay, that's going to tell us what exact formula you're going to use. So if you have F net, or if they want you to calculate F net, then you need to use the corresponding formula. Okay, and remember, impulse we're dealing with, and then impulse can be broken up as P final minus P initial, that's where your momentum comes in. Okay, so conservation of linear momentum. Firstly, we describe linear momentum as a vector quantity with the same direction as the velocity of the object. So if the object's velocity is to the left, the direction of that object is traveling to the left direction. Okay, then we can talk about conservation of linear momentum. Now, conservation of linear momentum, you need to know the definition, and its understanding is important for many questions, right? So the definition is, in an isolated system, let's maybe do this so it doesn't look like an L. Okay, in an isolated system, total linear momentum is conserved. That is the definition of conservation of linear momentum. Delta T is the rate of change of time. Then why do we just put the time given? Okay, I'll explain that. I think you're talking about specifically in questions. I'll keep your question up and I'll explain it. If I forget, just remind me. I'll explain it when we're doing a question. Okay, so yes, in an isolated system, total linear momentum is conserved. For most, what do you call these? I forget, but like you have conservation of, I'm forgetting. Conservation of mechanical energy. Okay, conservation of mechanical energy. All of the conservation definitions follow the same thing. You're saying in an isolated system, whatever the thing is conserved. Okay, so let's look at linear collisions. Now we're dealing with different cases for different questions. Okay, now case one. Let me just get my notes. Case one, okay, is separate to separate. So in case one, remember, this is a collision. So these two objects are going to knock into each other. So we're dealing with object A and object B. So object A and object B initially are actually moving towards each other. Okay, so object A is moving to the right, object B is moving to the left. And after they collide, object B moves to the right direction. So they basically move in opposite directions and they are separate. So we're going to call this case, just a simple term, separate to separate, so that we understand. Case number one, when the objects are initially separate, they collide, and after collision, they are separate again. So only give one variable, should we use simultaneous equations? Okay, again, that's a tricky question that's specific to the question. It's difficult to say. It's difficult to say right now. Okay, but we'll do some examples and we can go through it, right? So separate to separate. So when the objects are moving towards each other, they collide, and after collision, they move apart. Then we look at case two, separate to united. So the objects are moving towards each other. Okay, and initially before collision they are separate, but after collision they unite. So in this case you can see that object B, okay, let's look at in case one, this was 2 kg, this was 2 kg, they were equal in mass. Sorry about that. Okay, but in this case object B now is 20 kg. So obviously if it's coming with a certain velocity and it's a heavier object, it's going to now take this 2 kg with it. So now they both move together to the left. Okay, so separate to united, that's what it means. Then we have case number 3, which is united to separate. So like a train, like a cable car. In this simple example, these two carts are attached to the string, and after a certain type of collision, they are now separated. Okay, so initially, so now this guy is moving in that direction and this guy is moving in that direction. Okay. Let us talk about conservation of linear momentum one more time. We are going to indicate a formula quickly. So conservation of linear momentum means that linear momentum is conserved. So essentially, I'm going to put the sigma sign, which means the sum, okay, because remember we're dealing with two objects, so we are adding their momentum. So the sum of the momentum before is going to be equal to, again, the sum. Why sum? Because we're dealing with two objects, of the momentum after. This is collision. This, when we add up the momentums of both objects before, it has to be equal to the addition or the sum of both of the objects' momentums after. Okay, so that is the formula for conservation of linear momentum. Yeah. Let's talk about case one specifically and discuss the formula. So yes, it is all linear momentum. So sum before of momentum before is going to be equal to the sum of momentum after. Definitely. When we talk about the formula, okay, we are adding the momentum of both objects before, because we are dealing with two separate objects. So I'm going to calculate momentum for object one initially. This is momentum, mass times velocity of object A, sorry, not object one, the initial momentum of object A. I'm going to add it to the initial momentum of object B, and the sum of that has to be equal to the sum of the momentum of object A after. So V final, okay, added to the momentum of object B after as well. So for this specific case, in fact, for all cases of linear momentum, technically you can use this formula and it's going to work. So the momentum before of both objects is equal to the momentum after of both objects combined. Let's talk about separate to united. So again, we have this same concept because it's all linear momentum. We have the same concept where the sum of the momentum before is going to be equal to the sum of the momentum afterwards. So just to simplify the formulas, because initially they are separate, I will have two separate momentum calculations, mass times velocity initial for A plus mass times velocity initial for B. But now, because afterwards they are now together, they have one mass. So what I can do is, sorry, they have the combined mass, but they have one velocity because they are moving together. They have one velocity. So I'm going to say V final times the sum of their masses, because now it's like technically one object. So this is basically like calculating momentum for one object, m times v. I just said v times m because now we need to add the masses. Will we ever have three objects colliding? No, most likely not. They might be, I'm just saying a possibility, like there has never been, but there might be a scenario where there are three objects colliding, but you will work with two objects at a time. Okay, so yes, in this case, when they are together afterwards, we put that combined mass momentum afterwards. Okay, will do. Okay, let's just finish this up. Again, this is united to separate. It's linear momentum. So there is conservation of the linear momentum. Linear momentum before and after is the same. However, initially, they are almost like one object. So they have one velocity. So I will take the V initial and multiply it by the sum of their masses. And because afterwards they are separate, they are two different objects, I do momentum for two different objects. So m times v final for object A, the bracket is just to indicate object A, m times v final for object B. Can you please explain the adding of masses and velocities again? Okay, so basically the reason you're adding, so remember this, mass times velocity is a momentum calculation, mass times velocity is a momentum calculation. It is momentum initial for A, this is momentum initial for B. This is a momentum calculation, m times v, it is a momentum final for A, and this is a momentum final for B. So the reason I am firstly multiplying masses and velocities is because I'm calculating momentum, and that is the formula. Welcome, Mr. Aizen from YouTube chat. And that is the formula for momentum, mass times velocity. The reason I add them is because conservation of linear momentum tells us that the sum of the linear momentum before is going to be equal to the sum of the linear momentum afterwards. So I need to add the two initial ones because I have two different objects, A and B. I add their initial momentums, okay? And I equate it to the final momentum of both objects as well. Okay? So yes, these are just, again, for any case of linear momentum, you can technically use the first formula. These second two cases, the formulas are just shortened for maybe a better understanding for some people, maybe for some people to take a shortcut, right? But it is better to work with those, it's less calculations. Okay, should we do this or should we do graphs? Let's do this. Okay, so just things that are important to note. Remember that during collisions, both objects have the same collision time. Delta T. They collide with each other for the exact amount of time. Okay, object car A hits car B. They collide with each other at the for the exact amount of time, contact time. Okay, the period of time where the two objects are in contact with one another before they separate again after collision. Okay, so please remember that during collisions, this is important for calculations, for questions, right? That both objects have the same collision time always. Now, again, these are all for during the collision, you need to remember. The force acting on each object, is the same but opposite in direction. That actually comes from Newton's third law. Newton's third law tells us that every object in the universe exerts another force on every other object with a force that is equal in magnitude but opposite in direction. So when two objects crash, it doesn't matter if one is stationary and one is 500 kilometers per hour, or if they're both 500 kilometers per hour and they crash, it does not matter. The main understanding of this is that no matter what the collision is, during collision, the force acting on each object is the same. So object A exerts a force on object B, and object B exerts a force on object A, and those forces are equal in magnitude but opposite in direction. Okay. Number three, the magnitude of impulse for both objects are the same. Okay, so maybe the previous point you knew previously, but now this is a momentum type explanation thing. You need to know that impulse also remains the same for both objects. Okay, so the magnitude for it also opposite in direction. Yes, one would be positive, one would be negative. Okay, but impulse itself, delta P, for both objects during collision We'll get to elastic and inelastic shortly. For both objects during collision, remains the same. Is the same. Sorry, the magnitude. Number 4, object with less mass is always affected more. So according to Newton's second law, F net is equal to m times a, where acceleration is inversely proportional to the mass. Okay. Remember, F net is constant. Now we are talking about two objects colliding. One is heavier, one is lighter. The fourth point says that the object with less mass is always affected more. Now, if you think of a collision of a car and a bicycle, right? You would think that the car exerts more force on the bicycle, but that's not true. Okay. The reason that the bicycle guy goes flying into the bush and the car just remains unfazed is because of this reason. It's that the object with less mass, which is clearly the bicycle, is always affected more. And the reasoning for that is stated in the next point. According to Newton's second law, F net is equal to m times a. We should know that. And when we are saying acceleration is inversely proportional to mass, provided that F net is constant. Why is F net constant? Because of Newton's third law. F net is constant in this case because the objects exert the exact same force on each other. So the net force is not changing, okay, between the two objects. So therefore, acceleration is inversely proportional to the mass. So the smaller the mass, the higher the acceleration. Okay, so that's why the bicycle guy goes flying and the car remains still, because the bicycle has a lighter mass, and therefore it's going to have a higher acceleration. And of course, a higher acceleration, according to the formula, A is equal to delta V over delta T, change in velocity. Higher the acceleration, higher the velocity as well. So the rate of change of velocity is higher as well. Okay, so that's important things to note during collisions. You might forget it. It makes more sense, I suppose. To remember, it makes more sense when you do the question, and you'll see in what cases you need to remember it. Okay, let's go through why are airbags in cars necessary, which is a theoretical aspect of momentum that you are required to know. But according to delta P is equal to F net times delta T, F net is inversely proportional to delta T. Delta P is constant. Okay, mass and velocity is constant. Okay, that's why the change in momentum or the change in impulse is constant. All right. So in that case, since delta P is constant, the net force and the contact time are, so this remains constant, then these two are inversely proportional. As one increases, the other has to decrease because that needs to remain the same. Okay. So again, with the theory aspects, you need to just memorize most of it and understand it and memorize it, right? The chances they could ask it, they couldn't ask it, but you need to know it. Okay, so basically, yes. Okay, so F net is inversely proportional to delta T. The implementation of airbags in a car increases the contact time. Okay, the higher the contact time, the smaller the force on impact, and therefore the less the likelihood of injury. So the airbag increases the contact time because you are not knocking onto like the steering wheel or to the glass or to anything at a rapid pace, right? Remember, the airbag is sort of like a cushion, and when you impact with it, it actually your contact time with the airbag is a lot longer compared to your contact time with the steering wheel, where your head would just literally bounce off the steering wheel. So when you increase that contact time, okay, it actually decreases the force according to the formula above. Okay, and therefore the smaller the force, of course, the less the smaller the injury, or the less the seriousness of the injury, or the less the likelihood of injury in general as well. In the final exams, do we get questions on this year only or from grade 10? Okay, so I have a question. It says, in the final exam, do we get questions on this year only, meaning matric work, or from grade 10 as well? Look, you're not going to get any topics from grade 10. All your topics are from matric and are learned in matric. However, there are basics and understandings and fundamentals from grade 10 that you have to know in order to know many things in grade 12. Okay, so let's talk about elastic versus inelastic collisions. So again, we've been discussing collisions this whole time. Now, there's another aspect that you need to understand, you need to know, and that is elastic versus inelastic. Okay, so firstly, inelastic versus inelastic, elastic versus inelastic, sorry, we work with kinetic energy. Okay, that's the first thing that you need to note. And with an elastic collision, okay, the kinetic energy before, or the sum of the kinetic energy before, because remember, we are dealing with two objects that are colliding. So when there's an elastic collision, we can calculate their kinetic energies before, add them up, and that would be equal to their kinetic energies afterwards as well. Okay, we'll do an example, of course. I just wanna, what did I want to do? Yeah, remember that EK is equal to half mv squared. Okay, so you need to know the mass and the velocity in order to calculate the kinetic energy. And in most momentum questions, we have at least, we have those, especially if we need to calculate whether it's elastic or inelastic. Okay, however, with inelastic, right, the sum of the kinetic energy before is not equal to the sum of the kinetic energy afterwards. Why? Because some of that energy is lost during contact. Okay, I'll add that in the notes. I'll add it neatly before I send it to you guys. Okay, so some of the energy is lost during contact. So elastic collision, if you think of an elastic collision, it's like elastic collisions are actually not very realistic, right? Generally, when we deal with any collision on Earth, it's mostly inelastic, right? So that's what you need to remember. EK before is equal to EK after for elastic. EK before is not equal to EK afterwards in inelastic. Okay, so let us go into graphs, and then hopefully we're going to get to one question, right? So I'm going to answer this question from this person that asked earlier. They said that delta T, which is change in time, so time final minus time initial, is the rate of change of time. Okay, that's not true. Oh, yeah. It's not the rate of change of time, but it's just change in time. Delta T is not rate of change in time. Delta T is just change in time. Okay, what I mentioned here was delta T is rate of change of whatever if you're putting delta T in the denominator, whatever is in the numerator, because you have delta T in the denominator, you are describing its rate of change. So in this case, it's the momentum, rate of change of momentum. Sorry, rate of change of impulse. Okay, so but then why do we just put the time given? Generally, we put the time given because the initial for the time is 0. So like, for example, here, if we want to know what happened at that point, or how long did it take to get to that point, we just say 0,4 because we know that this is 0. So the final minus the initial is equal to 0,4 minus 0. Okay, in that specific case, if you are talking about at this specific point, right? So that's why we mainly just, even though it's delta T, we don't, most of the time, like you'll see in this question, that's not the case. We actually have to do a T final minus T initial. But most of the time we don't do that because the T initial is 0. Okay, we're going to get to that now, and we're going to show you how to understand graphs. Okay, I hope I answered your question. Okay, let's look at this graph. The first graph that we're going to learn is a momentum versus time graph. So we can see P, which is momentum, versus delta T in seconds, and then momentum is in kg, meters per second. Just one thing I want to show you. So remember, mass is kg and velocity is meters per second. That's how we get kg meters per second. One more thing is this formula actually creates another unit because it's force times seconds. We can utilize newtons per second to the -1 as well, because it's force times seconds, so newtons per second. Okay, let's have a look at this. Okay, so we have an example here. It's a momentum versus time graph. It's saying that we should use left as positive. Okay, so object B is stationary and object A bumps or collides into object. Sorry, I read that wrong. Object B is stationary and object A collides with object B. Okay, so whenever in your momentum versus time graphs, right, whenever you see a change in momentum, okay, it's either a change in speed, but a lot of the times if you see a drastic change in both objects, actually, that is where the collision occurs. That is where you should identify the collision has occurred in the graph. Okay, so initially this object had a momentum of 20 kg meters per second, and all of a sudden at 0,4 seconds, it drops. In a certain amount of time, it drops all the way to 8. So we can assume that is where the collision has occurred. So the first question is, calculate the force exerted by A on B. So before we even think of anything to do for this question, I just want to discuss when they say calculate the force exerted on A, or sorry, by A onto B, remember Newton's third law. The force exerted by B on A is the same. The force exerted on A that A exerts on B is equal to the force that B exerts on A. So if you can calculate one, you know the other one. Okay. Okay, cool. So now we have, they want us to calculate the force exerted on A by B. So we need to use force firstly. Force comes from delta P is equal to F net times delta T. Now, delta T we know, okay, remember, impulse we use for collision. So we need to know how long is the collision. So can someone tell me in the chat, how long is the collision? What delta T do we use in this calculation? Okay, correct, 0.4 seconds. The reason we use 0.8 minus 0.4 exactly. So for the person who asked about delta T, why do we always just use the time? Given that we don't calculate anything. In this case, we are doing a delta T. We are doing a final time minus an initial time. Okay, there's no calculation need to be shown for that, but that's technically what we're doing. So the collision happens for 0.4 seconds, right? They want us to calculate the F net. Now, the object's change in momentum or the object's impulse. Now, you might be used to, if you've done this already, you might be just automatically being drawn to use this formula. Okay, but the reason we will not use that formula in this case is because we are not given mass, firstly, nor are we given velocity. So how can we even use this formula? What we are given is momentum, however. We are given momentum. So again, we use this simple, seemingly simple formula, P final minus P initial. Because we do have P final minus P initial. Remember, the final is after collision. The initial is before collision. So after collision is here, and before collision is there. So we, instead of using this formula, we are going to use P final minus P initial. Because those are the values we given. So the final momentum is actually, okay. So direction is important. 1 second. Okay. How did we get the time? Okay. So the time we got, because we are considering contact time, so it's the time of collision. So it's between here and here. So between 0.4 to 0.8. So we said 0.8 minus 0.4, and that's how we got the contact time of 0.4. Okay. So now we have to consider P final minus P initial. Okay, so this is simple. Our P final is 8 kg meters per second. So P final is 8 from the graph directly. All right. Then we have P initial. Okay, I see a correct answer in the chat. Then we have the initial 20. Right, let's look at it more carefully. After collision, before collision. After collision, it was at 8 kg meters per second. Before collision, it was at 20 kg meters per second. Okay, so 8 minus 20 is equal to F net times 0.4. Here we get negative 12, and I take that over, divided by 0.4 is going to give me my F net. I get F net as negative 30. Remember, in physics, negative represents direction. In this case, they said that left is positive. If left is positive and I'm getting a negative answer, that means that it's 30 kgs to the right. 30 kgs, 30 newtons. Correct. Okay. So change in momentum is equal to F net times delta T. Change in momentum, yeah, we calculated by P final minus P initial. And we utilized the contact time and we did the calculation and we got a net force with a direction. And because they gave us the direction that's positive, we got a negative answer, so it's opposite. So because positive is left, negative would be to the right. Number 2, find the momentum of object B after the collision and draw the graph. Draw the graph for object B is what they're telling us to do. So find the momentum for object B after the collision. So remember, they want us to calculate P final momentum. For the person who asked, how do you know what to calculate? Again, in the first one, they asked for net force. This one, they're asking for momentum final. Remember. So the only formula that momentum final is in is that P final minus P initial is equal to change in P. Okay. Now we have P initial. Why do we have P initial? Firstly, because they tell us that the object is stationary. So if it is stationary, its velocity is 0. If its velocity is 0, obviously its momentum is 0 because momentum is calculated by saying m times v. So its initial frequency, its initial momentum is 0. What about its final momentum? That's what they want us to calculate, P final. So of course, in an equation, if you want to solve for a variable, you only need one variable. You can have two variables. So we need to have impulse. How do we get the impulse? How do we know the impulse, people? Someone tell me. How do we know the impulse of object B? When we don't know its initial momentum. Okay, F net times delta T. Sure, we could do that. Okay, F net times delta T. But you see, the key thing here is to understand this. Number 1, both objects have the same collision time. Number 2, both objects have the same force exerted on each other. Okay. Number 3, both objects have the same magnitude of impulse. So yes, your F net times delta T is correct. It's equal to the momentum, no. Negative 30 times 0,4, that is F net times delta T. Yes, the lesson will be available afterwards. Wa alaikum salam. Change in momentum, we already have it, correct. If right is chosen as positive. Okay, so the main thing, yes, okay, we could say F net times delta T, and then we say that F net, of course, is the same for both objects, but because we already have the impulse, we could use the understanding that, okay, impulse is the same. So therefore, since we already have the impulse, remember, it's same in magnitude, but opposite in direction. We already technically calculated the impulse here. That negative 12 is the impulse. Okay, or you could, maybe it's better that you say force, because we calculated the force as well, right? So force times delta T. Remember, this is negative 30. Now, the force on the other object is going to be positive 30. Okay, I hope that makes sense. So you could use both methods. So delta P, you could substitute positive 12 because the impulse of the other object is negative 12. The impulse of this object is going to be positive 12. Alternatively, we could say P final minus 0 is equal to F net times delta T. And that's going to be positive 30, not negative 30. Positive 30 times 0,4. Remember, they're always opposite. Same in magnitude, opposite in direction. And then we get an answer of 12 kg, positive 12 kg meters per second to the negative 1. Why can't we use simultaneous? How would you use simultaneous? I don't think simultaneous is necessary for this question. Could you please repeat 2 again? No problem. So find the momentum of object B after the collision and draw the graph. Okay, we need to draw the graph still. So find the first part. Find the momentum of object B after the collision. So that's P final. Okay, we only know one formula that actually breaks down P final, and that's delta P is equal to P final minus P initial. So that's the formula we're going to write down and see if we can solve it from there. Okay, so let's talk about object B, right? So in number one, they say calculate the force that A exerted on B. Remember, A exerted on B, technically we should be using object B's information because we need to know the force exerted on object B. However, we don't have any information except the initial momentum of object B, okay? The reason for that is it's not given. We don't have the graph for it. However, for object A, we have the graph, okay? We have a graph for object A. We can see object A's initial momentum and object A's final momentum. So we utilize that information to get the net force that each object is exerting on each other. Again, remember, it didn't matter, okay? Because it didn't matter because they exert the exact same. Sorry, it didn't matter because they have the exact same impulse. So we could use the impulse for object A and calculate the force. Okay, it would be the same answer. Now, let's talk about find the momentum of object B. Actually, I just want to correct something quickly. They say calculate the force exerted by A on B. Because they are asking us to calculate the force exerted by A on B, this will actually be to the left. It needs to be opposite of what we calculated. Because remember, the information that we used here was for object A. So this is the force that is acting on object A. This is the force on object A. We want the force on object B. That's what the question asked for. So it's going to be equal in magnitude, opposite in direction. So the force exerted on B would be to the left. Okay. Isn't it negative final P plus initial P equals change in momentum? Not always. Generally, you just use why do they sometimes use the quadratic formula? Is that for vertical projectile motion? Yeah, that's probably for vertical projectile motion. Okay, just to clarify number two, there's another question. Why is it positive? They're asking why is this positive? Okay, so yeah, so remember that for the net force acting on object A, we got negative 30. And for the impulse on object A, we got negative 12. Both of them we got negative, right? So for the impulse and the net force that's acting on object A, we got negative. So now when they want to know the momentum of object B, okay, we're utilizing P final minus P initial is equal to delta P. Now the delta P we know because it's impulse, and impulse remains the same for both objects, okay? But remember that impulse remains the same for both objects, but only in magnitude, opposite in direction. So because the impulse for object A was negative 12, the impulse for object B is going to be positive 12. Okay, let me just explain one more time. I understand where you guys are coming from. So let's read the question, right? The question says, calculate the force exerted by A on B. A on B. So when we say A on B, we are talking about B, okay? We are focused on object B, and we are focused on the force that is being exerted onto object B. So if you want to calculate the force exerted onto object B, in the impulse formula, you need to use B's information, okay? Then you'd get the correct direction for that force. But in the calculations, because we have no information about object B, we are using the information of object A, which is fine because the impulse is the same and the net force is the same, okay, but opposite in direction. So keep in mind, the information that we're using in the calculation is for object A. So when we get this final answer, this answer is magnitude and direction for the force exerted on A. Oh, I see, you're right. Oh, okay, I see. Okay, so it's for the force exerted on A, right? So the force exerted on A is to the left. Okay, I don't know why I redid it when we did it right the first time. Sorry. Okay, the force exerted is to the left because it's negative. So it needs to be opposite for object B. I already explained it earlier. Sorry. There was no need to do a correction. So therefore it's to the right, opposite. Wait, no. Wait. Negative is to the right. Negative is to the right, guys. Positive is to the left. Remember, if we are getting a force that's negative, this is firstly for object A. Secondly, it's to the right. It's for object A. So therefore, the F net on B would be equal in magnitude, 30 newtons, but opposite in direction, therefore to the left. Does that make sense? For those who were still thinking it's to the right. Does that clarify it? Okay, good. Okay, so it's a bit tricky, right, to understand it, but because our calculation is done on object A, that direction is for object A. But the question, and they try to trick you like that often, the question is actually the force exerted by A onto B. Okay, and yes, you can use the same values in your calculation because force is the same, impulse is the same, force is the same, impulse is the same. All right. Okay. Okay, then let me explain. Let me just look at this question. Doesn't depend on your convention. Direction was given in the question. Direction was given in the question stating that left is positive. I think that answers your question. If it doesn't, just ask it again, please. Okay, let's just revise number 2. So we're not going to go further. Sorry, I know we're starting off kind of slow. Eventually, we will try and finish each topic for the first term. Next week, what we'll do is we'll finish this question. More questions on momentum, like actual questions on momentum, not graph questions. And we will start vertical projectile motion. Okay, but let's just quickly revise this before we get too late. But okay, someone wanted to revise number 2. So here we go. They said, fine. Okay, so number 1 clarified. All right. Number 2, find the momentum of object B after the collision and draw the graph. Okay, so when we talk about momentum after the collision, remember, okay, firstly, we're working with object B. So now in your head, you need to think, okay, object B has a positive F net. The person that asked those questions in the Q&A, just let me know if I answered your question or if not. Okay, so object B has a positive F net to the left, and it has a positive impulse to the left as well. Okay, so in that case, you need to remember its direction. So you need to know whether it needs to be negative or positive. And you also need to remember its magnitude. Well, you can copy its magnitude from the previous question because both objects have the same magnitude of impulse and both objects have the same magnitude of net force. So if they want us to calculate the final momentum, okay, this is the formula we know with final momentum, so we write it down. P final is equal to P initial, P final minus P initial is equal to delta P. Now, P final is what they want. P initial, from this information that object B is stationary, we can say that the momentum initially is 0 because it has no velocity. Now, its impulse, again, we have no information, barely information about object B, but we can use the impulse of object A because during collisions, impulses remain the same. Okay, however, they are opposite in direction, equal in magnitude. So this impulse is negative. The impulse for object B is positive. For the person who asked why is it positive, that's why it's positive. And therefore, when we do the calculation, like I said, yeah, alternatively, you could use F net, right? And then you're going to use a positive F net and not a negative F net. And you're going to get a positive answer that your final momentum for object B is 12 kg meters per second. How do we draw that? I'm going to get to your question in a second. How do we draw that? Let's use this. So we're going to start off at 0. Okay. And it's completely stationary until when? Until the onset of collision. So until here. After collision, remember, collision is 0.8 seconds. I mean, 0.4 seconds. It's the same for both objects. So after the collision, its final momentum increases to somewhere like here, which is 12 kg meters per second. Then we can assume that it continues at a constant velocity. Okay, cool. Okay, so that's done. I'm just going to answer this last person's question and we're going to end it. So yeah, what we'll do next week is, again, we'll finish this question on momentum, the graph. We'll finish more questions, like actual questions on momentum, and we will start vertical projectile motion. In this question, we were given direction, but if we do not get direction, another question, how would we know if our direction is right? Okay. If you are not given direction, okay, so is this your new question? You said I didn't answer your question. Do you want this specific question answered? I'm going to answer this question, right? So if you are not given direction, they cannot expect you to answer a direction. You're going to have a positive and a negative. So you can say positive direction or negative direction, right? Alternatively, depending on the question, I'm just trying to think, if you get a positive answer, they don't give you direction. They wouldn't ask direction, okay? But in most cases, you'll see when we do and when you do examples, in most cases, there is a direction. Like this person is moving to the right, this person is moving to the left, they're moving up, they're moving down. So that in their final answer, when they're asking answers from you, if they ask velocity, if they ask a vector quantity, right, it obviously indicates you need to give magnitude and direction, then you'd be able to give a direction, right? If they don't give you direction, you just assume one negative, assume one positive. You don't have to assign, okay, positive is right and negative is left, or positive is up and negative is down. You can just assume one positive, assume one negative, okay? But in most cases, the calculation will already do that for you. Okay, and just like also remember that if you get one is positive, remember that the other one is negative. Like in this case, we didn't choose whether to get a negative impulse for object A's impulse. The calculation gave us a negative impulse. Okay, and then because we got a negative impulse for object A, then we just automatically, of course, the impulse for object B is positive. Okay, I hope that answered your question. I'm not sure yet. Of course, like eventually we're looking for both. They just discussed maths for now, but let's see. Yeah, it takes time, but let's see. Okay, I mean, no problem. Okay, so I'm running late for the next class, so I'm going to end it here. I'm glad that you guys learned today. That's really good. I'll see you guys next week. And like I said, with maths, I'll try and send you guys a timetable in the week so that we know going forward. Yes, the classes should be for people who like in June. I'm not sure if we'll be able to get to all topics by June.